All right, so we should go ahead and get started. I am very pleased to introduce Professor Gail Murphy from Computer Science at UBC. She's a professor in software engineering, and her area is in empirical software engineering and in analyzing the habits of software developers, which a lot of people are into these days. There's a lot of work on using machine learning to analyze software artifacts and repositories for information about how to make developers productive. But her group actually goes the extra step of taking that knowledge and trying to develop tools that actually do help make the developer more productive. So she does have a huge list of awards. I'm not going to list them all because otherwise I'd be doing all the talking instead of she. But I do want to list a few big ones, like she's a Killam Fellow, an NSERC Stacie Fellow, and then also a Fellow of the Royal Society of Canada. So welcome, Gail.
Thanks, Joe. So is the mic working okay? Can everybody hear in the back?
The mic actually isn't for them. The mic is for the video.
The mic should be for them because I don't actually have that loud of a voice. So it's really great to be here. I was actually in Waterloo 2 weeks ago for the Waterloo Innovation Summit, and I was totally blown away by how much activity there is in this corridor in Waterloo. I always knew that there was a lot going on, but coming here and seeing the breadth of expansion in computer science and engineering and in innovation in the space is really pretty cool. So, there's not a lot of perks about becoming a senior faculty member, but one of the perks is actually the fact that you get to come and do talks like this. And as much as I like talking about the research that goes on in my research group, I thought I'd take the opportunity today to kind of reflect back a little bit on the kind of software engineering research that we've done in the space of software engineering tools, and try and tease out a little bit about what makes it research versus the plethora of tools that exist to help with software development. So take it in that vein. I'm not going to go deeply technical in any area, but talk more about kind of what it means to do software engineering research in this part of what software engineering is about. So I wanted to start by dealing with the human-centric part of the title. So what do I mean by that? Well, I mean, one way, if you read the popular press these days, you might say that...
Clarification.
Yep.
I'm talking about human-centric tool or tools for human-centric software.
I'm going to get to that. Okay? So I'm going to clarify what I mean by it. Okay? So one thing that you might think if you see this title and you think about how software is going to be developed, you might say AI and deep learning are going to take care of this. It's okay, people aren't going to write software anymore. The bots are going to generate the software. And my assumption through this talk is really that at least in my lifetime of my career, that's not going to happen. And it's still going to be the people that are writing the software. So what we need to pay attention to is providing the people the tools that help fit with what they're trying to do, as opposed to focusing too much on the tools, which is where I think we've been. So the quote I have up there on the screen is from an essay that Mark Andreessen wrote for the Wall Street Journal a couple of years ago, where he was just elaborating the fact that there's more software needed in the world than our ability to produce it. So software is kind of eating us up, and we have to figure out ways to make people more productive, train more people, but also make the people we have more productive in writing things. So I usually like to start my talks with the end. So what I want to give you is an encapsulated summary in 2 slides of everything I'm going to say, or at least an abstract of that. So if it's late in the day for you and you need to doze off, you can feel free to, and you'll already have the punchline, be it what it may. So if we think about this space of tools for helping build software systems, I'm going to divide that space into 2 parts. The tools that are effective for the people using them, and the tools that I'm going to claim are not very effective for the people. They have to use those tools sometimes, but the people have to do more work to use the tool than the tool is really helping the people. So what do I mean by that? Well, what would I put in effectiveness? I'd put things like editors. They're pretty effective tools, right? That's Sublime. People like Sublime. I put tools like GNU Make, because we all love Make, those of us who are senior, right? It did a lot of work for us without the people having to do a lot of work to use it. So what goes in non-effective? I'm going to put lint there. I'm sure there's people here who love lint. But was lint a super effective tool for people? I'm going to claim no, because it tends to provide so many false positives that the people end up doing work to look through the results more than the tool just providing the results that people need. I'm also going to put in that space some of the non-trivial refactoring tools. So if you go into a development environment, there's lots of really fancy refactorings. If you look at the logs of people using those development environments, they don't use them. And there's lots of reasons they don't, but one of them is that they're really actually pretty hard to use. Within these two spaces, there is a subset of both effective and non-effective tools, where I'm going to claim that in software engineering research, we know something about maybe why they're effective or not effective. I'm going to say that theories help guide us in making those choices. So in that area, I would put things like a tool called the Y-line that you may or may not have heard of, but it was Andy Koh's PhD dissertation. And the idea was, instead of providing debugging tools that let you look at things like variables and step through programs, why don't our debugging tools let us ask questions about why the program didn't work in those phrases? Why is this box orange instead of blue? And he built a tool that used a lot of static analysis and dynamic analysis underneath to allow you to ask those direct questions and get results. I'm going to claim that's a very effective tool where there was a theory about why it actually works. We also know that things like the extract method refactoring actually don't work very well for people. So this is a refactoring where in a development environment you have a really big method and you highlight part of it and you say, I want to actually extract this method automatically into a new method. It turns out that there's a lot of problems with the interfaces that we provide people for selecting the right code and setting it up, and they make a lot of errors. They make enough errors that's probably easier for them to copy and paste it than to actually use the tool. And a tool I'm going to talk a lot about in this talk is a tool that came out of my research group called Mylan. I'm going to use it as a running example. And it's a tool that helps to try and bridge between just the information people need to do a task and what's provided. So here's the punchline. So what do I want you to take away from this talk? I'm going to try and convince you that there's really, oh, it didn't actually go. That's the research. There's 3 different parts. One part is about identifying what are the mismatches between how people think about software and what they need to do and the tools that they use. So one part of trying to do software engineering research in this space is identifying those mismatches between how people actually think and work and the tools that they use. The second characteristic you should look for in software engineering research is some sort of theory that helps you bridge between what you're saying is going to help and the actual results. And the third part is that once we have those 2 things, we actually have to assess whether or not the tool that we're saying is going to do something for the developers really does it. Now, it'd be nice if we could just put developers in a chair and say, did this work for you or not? Turns out that that experimentation is fraught with a few more difficulties. So if you remember anything, 3 characteristics to doing research in software engineering tools. These are the 3. It's all about figuring out why things work and why they don't. So how I want to take you through that is to start by talking a little bit about the context of the problem. We all know how software gets developed. I'm going to force you to think through it again, just so that I can explain some of the terminology I'm going to use. Once we have some context of what we're interested in doing, and then we can start to look for these mismatches between how people work and the tools that we're giving them to do that work. Once we've got the mismatches, we can start thinking about the theories. What might make it better? How might we bridge between what we're providing them and what we're showing them? Then there's that assessment piece. I want to talk a little bit about that before I actually do some summary of what's going on. And as I said, through this, I'm only actually going to use one technological example, which is the example of this Mylan tool that we built within our research group. It became part of the default part of Eclipse, and we've now built a company that's been running about 9.5 years based on the technology. So I think there's some things that hopefully I can tease out by using that example. So let's start in with this context piece. Clearly, many interesting software systems aren't developed by individual software developers, right? It's groups of people working together. And certainly in Waterloo, you have lots of companies that require groups of people working together to make interesting things. So we always have to remember that there's always a greater context, even if we focus down on an individual, that those individuals work in teams, the teams work together, they might work within bigger organizational structures. But when you get right down to it, you do have an individual typically writing code. That individual has a particular view on the artifacts that might be code, it might be issues, it might be wikis, it might be different things that they're working on. What's really, really cool about software development is that so many of those artifacts that they work with are very structured. Sure, some are a little more unstructured, like when we have natural language and documents. But even there, we have substructures that exist of these documents that we can play with. This is really different than other knowledge workers, where they might not have as much structure. Lawyers certainly have some structure, but more of it is natural language. So we like to view in my research group software developers as kind of the prototype knowledge workers of how more people will work in the future. And because we have that structure, the information that they're working on really forms this large information space where we can take apart bits of documents, bits of source code, and we understand how they're related in these network structures. And that provides us many interesting opportunities to work with that information. And finally, software development also involves those individuals with their big information spaces that they're working with, working on the same information space, usually through some shared repositories or shared document spaces. And now what gets really interesting is the fact that changes are happening to the information space you're working with. So we did one study of a group of about 7 IBM developers over a period of 3 months. Turned out that if you look at an individual's workspace that they're using of source code, looking at the system they're building on, there were changes coming into that environment every 54 seconds of their working day. So that information space isn't static, it's always changing, and that makes the problem even more interesting. So that's kind of the context, right? People working together, people working on really complex things, and those complex things are always changing. So for software engineering research, why does that matter? Right? Well, when we narrow down to look at a particular problem or tool that we're going to put in to make things better, we need to try to kind of narrow the context so that we have a workable box to work in, to find the mismatches, to figure out where the theories might matter, to figure out how we're going to assess whatever we're going to try to make better. But even when we narrow in, we got to think about that broader context, because it doesn't matter if we solve somebody working with a particular problem in their source code, if that information is changing based on other people, and we have to take that into account. So in the case of this running example that I'm going to use of Mylan, what we were most interested in terms of context was an individual working with source code. So the only information space we really cared about at the beginning was the fact that they work on source code. That forms this very large information space of interconnected pieces of methods, documents, and other things that they might have, comments that they might have in the code. And that's really where we define the box. This is the context in which we're going to try to address a particular problem. We expanded that context a little bit as we started to investigate the problem. When people are working on source code, they don't just get to work on exactly the problem that they started working on at the beginning of the day. Because somebody on the team comes in and taps them on the shoulder or sends them a Skype alert or slacks them or does something and says, guess what? I've got a really hard problem. It's your code and you need to fix it. So they end up switching tasks. So their context of working with code is not, I am going to work on a problem for the entire day. For most people, they're working on an average of about 11 different tasks per day. And for every task, they're going to be flipping in between different source code files. So this is just a graphic of a study that we did where we looked at about 11 different software developers at 3 different companies. And we had a graduate student shadow a developer. So if you're a developer, they're sitting behind them watching everything on the screen, coding everything that happened on the screen. What were they doing? What task? What tool were they using? And trying to record all that information. They validated it by stopping the developer and asking them, but we kind of got a view on what they were doing. So every line is a different developer. This is 2 hours of the 4 hours we watched every developer. And the only thing that you need to take away from this is that there's a lot of different icons. Every icon is a different thing that they're doing. Every icon almost involves a different tool that they're using. And you can see that the flips are really, really quick, right? So not many people were sitting looking at an editor of code for a long time. They were flipping between a lot of different activities. The gray bar, the gray shadings in any given bar are the different tasks. So you definitely have people like down here at the bottom here who are switching between about 3 different tasks, 4 different tasks in that 2-hour period. One thing I always take away from this diagram is clearly developers are a little bit hyperactive, at least the ones we were watching. Interestingly, when we asked them if they were productive during this period, of course they thought they were incredibly productive. So what do I want you to remember? Myelin is about source code. It's not one problem at a time, it's multiple tasks. So let's take a little bit of a look now, given that context, about the mismatches in this space. So we've got our developer. They've got an IDE up. They're looking at code, working on a particular bug that they need to fix or feature that they need to implement. What they're looking at in terms of source code on the screen is what they're going to change, but what's going on in their brain is more something like this, right? It's more piecing together how are the functions or the methods that I'm working on, how do they connect together? If you sit behind developers watching and watch them fix a bug, a lot of it is traversing a bunch of methods. How are they actually connected? How is the data flowing? And if you talk to them about what they're doing and have them draw pictures, which studies have done, they're drawing network structures. What's up on the right-hand side of the screen is just a call graph from a like 20,000-line Java program. It's still super complex. Nobody holds that in their brain. I think relatively few people hold that in their brain. What they're trying to do is capture slices through these particular graph structures. So those information spaces are really complex. What our tools do, this is Eclipse, but it could be IntelliJ, it could be whatever your favorite tool is. What our tools do is take a really tool-centric approach to showing you the information you have to work on. They're actually pretty amazing tools, right? You can throw 1 million lines of code into one of these things, and it will happily show it to you all in an Explorer view. You can throw 1 million lines of code into this thing, and you can happily do a search, and it will show you all the search results very quickly. So they're really interesting engineered pieces of software themselves. But for the developer, what they're getting is kind of this tool-centric approach of giving the complete information that you need. Here it all is, go to it as you, the human. What that means is you do something like a search, or you have warnings up here as problems, and you get results like, here's 100 items of 623 I'm showing you. So I don't know about you, but when I program, I'm not going through all 623. I'm going through the first one, fixing it, and see if it makes the other ones go away. So the question becomes, why were you shown that at all? What the interaction becomes of the person with the tool is something like what I like to refer to as this select, perform, scroll, and repeat. So what you end up doing is you get a piece of source and you say, I need to figure out where the X feature is implemented in the source code. So I might search. There's my sort of, I'm going to do some perform immediately. Now I get a big list, right? 623 search results. So now what do? I select one to look at. My whole screen changes of information because it's all reactive to each other. I take a look at it, I think about it, I scroll down some more results, I select something else, and I keep repeating this over and over and over again. And so my claim is that, let me make sure that I can get my screen up here. My claim is that what we're really doing is we're treating the developer a lot more like one of these guys. Somebody who sits there and bashes on the keyboard a lot. And actually, to be honest, I don't know I'm sure Waterloo students are way better than UBC students at times, but there are times where you watch a student program and it's totally empirical, right? It's like, maybe this will work. Maybe this will work. And it feels a lot like this is going on with our poor little monkey. So what I think our tools are doing is really making people do something called clickitis. They spend a lot of time clicking. They sometimes spend a lot of time clicking instead of actually thinking about what they're doing. And part of my claim here is it's not their fault, because that's what the tools are making them do. The tools are not really helping match how they think about the problem. The tools are taking this very tool-centric, information-centric viewpoint, saying, here it all is, go to it. And that's what I think we need to change. So this is exactly what we were tackling in Mylan. What we came to the realization is that if we look at the IDE, it's information overload. Virtually every pixel on the screen quickly becomes filled with information. There's icons that have lots of little overlaid icons on them, so that there's a whole icon language you have to understand. But if you watch people work, they don't care about all that information. They don't usually care about all the files that are located in the same directory as the file I'm changing. What I'm doing as I work is I'm only working with some pieces of that information, and a lot of the work is finding it. So we're constantly asking people to find just the pieces of information that matter for the task that they're doing. Remember, they were switching between all these tasks in the context of the problem. So there's a mismatch between showing everything when only some stuff is actually needed. So maybe, just maybe, there's a better way to do it. And one place where we can look for help is to look into theories, like I said, about how people work. So remember, I had these kind of 3 levels of context in sort of very generally speaking of software development. Teams working together, people working with complex stuff, people working on the same complex stuff. Now, there's theories out there that we can borrow from other disciplines that might help us guide us to better solutions. So things like social presence theory, that talk about who's the most important in a given conversation, might help us when teams are working together. Peggy Burnett at Oregon State has done a lot of work borrowing from some biology ideas and translating them into information spaces and talking about information foraging. How is it that people actually go look for the information they need? And by developing a theory around that, it can guide us in how we're building tools. And sometimes, because software actually does have some unique structures, we got to create some. So there's been a lot of work in the past about what really are theories about how people comprehend programs. Those have gone to the extent now that they're using various kinds of brain imaging to look at how people actually think about programs. And there's been a lot of great work in socio-technical congruence that took a look and said, gee, when the people are communicating similar to how the software is actually interconnected technically, when there's congruence between those two things, we get better quality software. So cool, we got lots of theories. Psychology has lots of theories. Sociology has lots of theories. We can make them up. So are we actually always using them? I'm going to make a slightly bold claim that I'm sure people are going to call me out in questions, but I'm going to claim that theories are just not always present, right? Sometimes we're not actually using theories, we just make tools, because tools are kind of fun to build. It's really fun to engineer these things up to work well. But we really do, if we want to do research in software engineering, we have to think about the theories that lie behind the tools that we want to build. So going back to my Mylan example, if you think about an IDE, and you think about how somebody uses an IDE, what it's really based around is taxing the semantic memory of individuals. So there's different kinds of memory models. Semantic memory is one kind of model that psychologists think is going on in our brain. And semantic memory is a multiple exposure model. We can remember things about the program if we see it over and over and over again. So I'm sure you've worked with programs where you just know where such and such a feature is implemented because you've done it 45 times. Those multiple exposures build up that memory and help us be able to find it. Dan?
But doesn't software itself tax the individual's memory?
Sure, and I'm going to try and subdivide memory a little bit just to drive the point that the theory actually matters. So absolutely, software is going to tax us cognitively in multiple ways. And we're going to have to use multiple memory models, for sure. So with the semantic one, we need these multiple exposures. The problem with the multiple exposures is if you're working on a really big system, your chances of being exposed to the same thing time and time again may not work that well. We're making people go and find information time and time again. We're treating them like the monkey instead of maybe finding a theory that matches a little bit better. So the idea that we really had behind Myelin was that we wanted to leverage episodic memory as well as semantic memory. And the idea that psychologists say of episodic memory is that it's our ability to associate things like elements of information with an event that help us recall the information that we care about. So, if you think about in the real world, it's pretty easy. Okay, sometimes I don't remember this. It's pretty easy to remember what you did yesterday, right? So sometimes when you're even trying to find a web browser page that you used previously, sometimes it's like, well, I remember I was searching for a trip at the same time I found that thing. And if only we could go back and really easily search for that episode of looking for something, maybe it would be easier to find what we're looking for. That was the idea with Myelin. Maybe we could tag the information that's important for a task together with the event of working on that task. And if we could tie these two things together, we could make it much easier for people to find the information and recall it than they might otherwise. So let me give you just kind of a brief demo of Myelin in action. And I hate it when my okay. So here we are. We've got kind of our regular package explorer, regular development environment where we can see all the information. So this is just an IDE working as it normally does. As we expand things, it becomes really hard to find them. With Myelin, we had a representation of tasks that are available within the development environment. And for the tasks, we can go back and recall one that we worked on before. And what it's done is it's brought back every piece of information that you had worked with as part of that task previously. And it had focused the interface to only show you what mattered. Everything is still there, so you can still get to the complete information. But with one click of a button, you can focus it in and say, just show me the parts of the system that mattered for this task. By doing it episodically, I can move to a different episode, a previous task I had worked on. And now it brings up just the code that I worked on for that previous task. So I'm able to tie the events of when I worked on a particular kind of activity together with just those parts of the information space that mattered for working on that activity. And so one important thing that I'll describe a little bit after the demo finishes is this tagging of information to the episode, to the task, is automatic. As you start to work with the information, Myelin is watching every interaction event that you have had with the source code. And it knows that you just touched a certain method or visited a certain method. And it says, hey, that's probably important for this task. I'm going to remember that. So the developer doesn't have to build up the model. The model just happens. What we did is actually tie together episodic memory and semantic memory as a theory. And so when you have a task activated and you're working with the information, the more exposures you have to a particular method, the higher the degree of interest we associate with that particular method. If you do not work with that method for some period of time and work for other information, we lower the interest we have in that. So the model behind the task is always ebbing and flowing. The more reinforcement, semantic memory that the developer is giving a particular item, the more important it is to associate it with the episodic task. The more it was just one of those methods that you worked with and went, yeah, this has nothing to do with what I actually need to do, the more it's going to fade back into the background. So it's using frequency and recency to build that up. So the important point here is that we're trying to flip the ID, we're trying to flip the tools to have a different theory that's driving it. So you can build that tool. Obviously, we did. And the question you should be asking is it enough just to build it? It'd be great because research would be a heck of a lot easier if you could just stop there. But I'm going to claim that the third important characteristic is that you need to assess whether or not that tool actually is effective for the situation that you were trying to improve. And in software engineering, we do a lot of different kinds of assessments. Super popular right now to do simulation studies. So lots and lots of work is being done on analyzing the repositories that exist, simulating something and seeing whether it matches the reality that it happened or it could be made better. That is a great place to get a certain level of understanding if your tool is actually working, and a really nice baseline to take a look at. But all too often, I'm going to claim that in software engineering research, we stop too soon. We stop with a simulation study, and we don't actually drive it through to seeing whether it works for humans. Because just because it worked when you run it against the repository again doesn't mean that the human can actually take the results. So you can imagine doing a study with lint, which I claimed was not effective, and saying, look at how many of the errors lint found that were eventually fixed. But when you put lint before many developers, they might not have the same experience. So there's also a need to be able to start thinking about different kinds of ways that we can try and understand how we match theories to what we're doing, to drive kinds of assessments that allow us to think about whether or not the theory is actually matching with what's going on. So in addition to these kinds of simulation studies, there's also a need to think through to how do we do case studies and experiments with people. Sometimes that's students in labs. Maybe some of you have participated in them. It's really great when we have a tool that we can actually put in the field in situ, because now we're able to match the context that we were talking about with what we were trying to actually study. And in fact, with Mylan, that's basically what we had to do. So when we were thinking about the assessments for Mylan, we were a little bit stymied for a while, because we really would have liked to just run lab studies, quite frankly. But where it's good is episodically. So you have to have episodes to test, right? You have to have things that resonate with the human as episodes. So you need these tasks. So maybe you could devise a lab study where you ask students to do a series of tasks and then you recall things and so on and so forth. But every advantage of the task is really only through multiple exposures to that task, which happen as people, as real developers, switch between tasks. So we came to realize that the real advantage was going to be a little bit all the time over a long period of time. And it's really hard to do a lab study that's multiple days long. We've actually tried in the past, and it was really painful. So instead, we said, let's just go to the field. So luckily, we had Mick Kirsten was driving this project as the PhD student, still the mastermind behind Mylan. And he is a stupendous programmer. So with a team, we managed to build up a tool that we could actually put into industrial use. And way back in 2004, we went in the same year, I think, from an idea on the whiteboard to trialing it at IBM with a small set of developers. And that was a fantastic experience because from the feedback that we got back, we were able to devise a user interface that really we thought could work for people. A year later, we wanted to expand that study. The industrial trial at IBM was like a week of 5 people. There's only so much you can learn from that. We learned a lot about the UI. So in 2005, we wanted to do a longitudinal field study where we wanted to measure how developers worked with information without Mylan and try and assess how they worked differently once they had Mylan installed. So we went to the EclipseCon conference, which was just starting up then. It was the large conference for Eclipse users. Mick gave a great talk, and he got 100 people to sign up and say, I want to try this. We said, OK, you have to understand, before you get to try it, you have to send us data of 2 weeks of your work. Then we'll let you use Mylan. So 99 still said, we're in, we'll do it. We shipped them the tool. We gathered a bunch of data about how they worked. Most of them, I think about 80 to 90 of them, ended up getting the Mylan tool after 2 weeks. They had to reach a certain threshold of working with Java, which is what the tool worked best with. At the end, we ended up with 16 people that used the tool enough over 4 weeks to have enough data to be comparable. The kinds of people we threw out were the PhD students using Eclipse to write LaTeX. Wasn't really resonating with us. And there was a bunch of people who ended up switching what they were doing, right? They programmed a lot for 2 weeks, and then it looked like they went into a planning phase and they weren't programming. So we ended up with 16 people where we had enough data. So we essentially had every click that they had done in the IDE for 2 weeks without Mylan, and every click and command and such that they had performed with Mylan. And then we took a look at how much more were they coding than clicking. Because remember, one of the sort of motivating theories behind this is people were the monkey, doing a lot of clicking and not doing a lot of coding. And we wanted to show that they were editing more than clicking. And it turned out in 13 of the 16 cases, their edit ratio, this ratio of how much they coded versus clicking, actually improved with Myelin. So that was a case where I think we got the assessment quite a distance, because we were actually able to show that in the context of real people's work, we had no control over their work, they were actually working differently with Myelin than not. And at this point, it's downloaded about 2 million times per month. So those are kind of the three things that I most wanted to get across. I'm sneaking in a little thing here because as I was making the talk, I'm like, I don't want to just summarize at this point. Yeah, there's a little bit more I want to say, so I'm adding an epilogue. So here's kind of where I started, right? There's tools. Some of them are effective. Some of them I claim are not. There's only a subset of those tools that I would consider that there's been research about those tools because we have some understanding of why. Remember, we don't know exactly why. We have causation kinds of issues. You know, when we put this in and we have this theory, we think there's some relationship. So you might be asking, well, okay, but there's other effective tools that aren't in the research bucket. So why spend all this effort doing research if we have effective tools that don't need research? And I'm going to claim that that's when often innovation is happening. I'm making kind of a sharp distinction between research and innovation that's not really fair, but bear with me for a minute. So how is it that we get these effective tools? And how can we actually, as a research community, do better in understanding those effective but not research tools? So let me take some liberties in diagramming, and I can't draw, so really give me some space here. Imagine, you know, we're always all building on top of a body of research that exists. Whether we're actually in academia or we're outside of academia, there's research that exists. We have access to it. Some of it is just baked into knowledge at this point. Inventions are usually considered as something that is the creation or design of something that didn't exist before. And that kind of comes out of research, right? I mean, you don't invent in a vacuum. You invent in the context of research that's existed. Thomas Edison is always the famous example of an inventor, things like the light bulb. We like the light bulb. I think when we were doing the Myelin work, when we came up with the data structure, I think that's when we actually had a bit of an invention. Not a huge invention, but we had a little invention. We could have patented it if we wanted to, I think. Not that that's the gold standard of invention. But that really came out of research, right? It really came out of our knowledge of how work had been done and what kinds of structures existed to work from. On the other hand, we've got innovations. Innovations also build on this kind of base of research that we have out there. And innovations are usually more about using something in a new kind of way, right? Everybody loves to use the iPhone. It's kind of the canonical, current example of an innovation. I'm going to claim that with Myelin, what happened for us is we had this idea of the data structure, this idea of being able to do semantic kinds of memory reinforcement through a frequency and recency type approach, represent that in a particular way. Once we had that idea, we kind of went back through research, thought about what other people had done, human-computer interaction research. And there was a day that I think I will always vividly remember, to be honest, when Mick and I were looking at the screen and we had a visualization that we had developed that we were going to build, that developers would have alongside their IDE to look at this different view of the information. We went, why would we do that when we could fold it in to the IDE and make things just go away? So the UI innovation really was about making things go away instead of providing something new. And we took that and we published that, and I feel like we were pushing things back into research at that point and making it available for other people to really build on. So in 2007, Mick actually finished his PhD, and I think he finished on a Friday. On Monday, we incorporated the company. We had been talking about the company for about 2 years before that, so it was a long transition period. And when we went to the company, I think things started to change in how we actually started building new things. And in some ways, we're starting to change this now, but when you get into that innovation phase and that sort of company building phase, you sort of get taken from thinking about research a lot into practice, and that's a really good thing, especially if you're a software engineering researcher, because you start to talk to people a lot more about who actually do things and start to understand what they actually need. So in 2007, we incorporated. In 2008, we took that Mylan tool that I basically showed you. It was open source. We put closed source connectors on top of it and sold it as a product. It was the recession. We continued to build the company out. We got a couple of enterprise sales. For about the first actually more of the first 7 years, we continued to develop products. So we realized talking to our customers that, guess what? It's really hard to get people to buy a tool that goes on software developers' desks, because now the IT department has to put that on everybody's desks. Now you have to train everybody about how to use it. It's a really hard road. But in talking to our customers, we realized that a lot of the data structures, a lot of the ideas that we had, could really be represented to help in a slightly different context. Instead of the individual working with their tool and the information in their tool, the same ideas apply to helping teams work better together. So we took the basic idea, took it from the desktop into server land, and instead of focusing on the information that we're showing to the developer, we also started a product that seamlessly connects the different tools that a development team uses. So if the requirements analyst updates a requirement, our Tasktop Sync product can flow that through to the developer and flow it through to the testers so they see that change in the context of their own tool. And so that provided us a much easier base to start to reach a broader market. We bootstrapped for 7 years, became about 55 people, and in 2014 we took our first Series A venture capital, which has allowed us to build out to about 100 people. But the point that I really want to make with this is that when we started to work more in sort of with the actual software developers, with the actual software development teams, it's not like we stopped innovating. It's not like we stopped inventing. We had innovations that were being driven up into the products that we were building. By having them used in practice, we had ideas and innovations that were flowing back. And we had new inventions that were coming out and being put into our products. But what wasn't happening is we weren't actually pushing those back to research. And so it's harder for other people to take advantage of them, which is kind of good from a company perspective, obviously. So we've got these two things that are always going on in parallel, especially in the domain of software development. We've got sort of software engineers, researchers typically out in academia, building really cool stuff. And if you hang around the software engineering academic community, you hear about bemoaning of a lack of transfer of some of that to practice. On the other hand, you've got a lot of people in practice that are building tools that people use every day, and they didn't come out of research. But I think what's important to remember is that both of these kinds of things are important. It's important to invent. It's important to innovate. What we need to do a better job is in part understanding how we can get those innovations back into the research domain. And I always like to try to remember this quote from Ellen Kay, that it takes just as much creativity to understand an idea as to have it in the first place. So there's a really big role to play in trying to understand why innovations work that we're not currently doing in academia. Because we're spending a lot of time getting students, in particular, to have inventions that give it driven down into the research base, and maybe not enough time saying, wow, why is it that Ruby on Rails is really popular? What is making that sort of a package mechanism, et cetera, from an architecture point of view so appealing? We don't spend a lot of time taking a look into that problem. I didn't actually do any of this work. I've been just totally blessed to work with a lot of amazing people. This is kind of our early Tasktop team and Mylan team. Some of them came into the company. Some of them went in other paths. 6 of those people are still with the company. All of the 3 co-founders still like each other. I'm really happy about that. This is an old picture where like double the number of people, but we've never actually all been together. and just a totally amazing group of students that have really influenced these ideas. So hopefully I've clarified a little bit about human-centric software development tools, and more importantly, what it means to do research in this space. And I think we need to do a better job of not just doing research about inventions, but research about the innovations that are happening in practice. Because there are tools that are widely used, and they're widely used for a reason, and we don't know why. So really, remember, it's about the why when we're doing research in this area. We need to understand where the tools do not work for the people. We need to come up with theories to understand why there might be those gaps. We need to build the tools that then take advantage of those theories. And then we need to figure out if they actually work. Thank you for your attention. And I'd be happy to take any questions, I think. There's one up in the corner here, Joe.
Just a quick comment. On the 3 slides beforehand, when you showed the team, you had Mylar and Tasktop.
Oh, yeah.
That had been Mylar.
Oh, yeah, I forgot to update that. So here's the really quick story of that. Let me get back to it. Oh. So in 2005, when we first released into open source, our tool was called Mylar. And it was called Mylar because it prevented information blindness in the Eclipse IDE. Okay, we liked the take of the Mylar film and the Eclipse. And then when it became part of the default download of Eclipse, we got lots of calls from the Eclipse Foundation lawyers who said, Mylar, DuPont and its holding companies, trademark. We're like, different domain. They said, no. So after conversations with Wall Street lawyers, we had to change the name. So the name became Mylan because it's like a myelin sheath. It allows you to code at a faster. Thank you. I always love telling that story, so thank you. Yes?
At some point, there was an evaluation, and I think the metric was edit ratio.
Yes.
And so is there some correlation between edit ratio and software quality, or?
We have not shown that relationship. So definitely all that edit ratio shows right now is you spend more time typing code than you spend actually looking for the code to work with. But that would be a really interesting thing to look at is, does it actually correlate? So one of the things that we do a lot in my group is research into productivity. And we haven't found the right metric yet. I don't think anybody has. But if people have ideas, I'd love to hear them. Yeah.
So you did the longitudinal study with the 16 participants. What was the metric that you were testing? As in, what was the baseline condition that you're comparing against?
So we were doing this edit ratio thing. So it was whether or not they spent more time actually writing code versus selecting code within the IDE, selecting methods, et cetera. So it was just simply that ratio of what was their activity in the IDE. Was it more about editing, or was it more about selecting and looking for code?
So does the writing code only represent the true measure of this, though?
I don't know.
Like if a source code having multiple files would eventually have multiple clicks anyway.
You do, but when you've got 4 weeks of people's activity, you can definitely see when they're editing more and writing more code. Absolutely, I believe that. The cases that we had trouble with and some of the people we threw out, one of the things that this relies on is that people are very active with the tool, right? They click on things, they edit, they're not just looking at the screen. So we have no idea whether they found the right code faster and just had to read the code a lot. No idea about that, because we had no visibility into that. Now, it turns out that with IDEs, you have to be very active. We did have people that, the arrow keys at the bottom? It's clear that when they read code, they did this, up and down, sideways, up and down. So you would look at the logs, and there would be 2,000 up and downs, right? We kind of threw those people out, right? Because obviously, they have a particular habit. But it's really interesting to see people are very active on the keyboard and the mouse. Yes?
Yeah, I'm just wondering how receptive programmers are in using your tool in an industrial setup, knowing that your tool is collecting data
Yep.
on whatever they're producing,
Yep.
and this data could potentially be used against them?
So interestingly, that's always come up. It typically lasts for about a day of somebody's use. We hear two worries, right? The first worry is, you're going to see all the code I looked at that wasn't relevant, you're going to think I'm a bad programmer. The second thing that you hear is, you know all my data, and now my boss or whoever can watch me, right? So we took a lot of pains actually to do a couple of different things. One is the data is always local to your machine. So in the field study we did ask people to share it. It was all anonymized. The code was actually de-identified. So we were guarding against that. But if you just use Mylan, it only sticks on your machine. Nobody else can see it. There's a slight difference to that I can explain, that you can choose to share it with your colleagues, these task context things that we call. The other thing that we did, because we faced it at our own company, is we were doing parallel open source and closed source development. And for every task that we were working on, we were posting the interaction history that we had into our open source repository. Well, there was source code that was closed that we were working on for clients that, yeah, we didn't quite want to share. So there's also an ability to go in and actually remove stuff. So there's a variety of safeguards. Interestingly, as people use it, they quickly get over that first hang up, right? I mean, I've literally sat beside people and they're like, oh no, somebody's going to see that I went to this file. Had nothing to do with it. It's like, don't worry, it'll fade away. And after about a day of using it, they're like, everybody does that, I don't care. Yeah.
So for your initial study with the 16 people at IBM versus
5 people.
Or sorry, 5 people with
Yeah.
IBM over the week versus the 16 people that you captured over a longer period of time. At the point where you were just working with people from IBM, did you get any feedback that pointed to your theory of episodic memory?
Absolutely. So what I didn't actually describe is the fact that when we put the tool into use at IBM, we actually only had this degree of interest model that allowed you to filter, and we didn't actually have tasks. So we didn't actually have episodic memory directly tied in. We knew from our own use that that was a problem. But when we had industrial developers like, you really need to have our tasks represented. We're like, great, because that's what we're working on. So that was a really nice kind of reinforcement for ourselves about that. May.
So in the ineffective tools, and you kind of pointed to static analysis, warnings.
I figured you'd recognize that, yeah.
A lot of warnings being shown. And that kind of is because, I don't think any static analysis tool is reducing the amount of warnings, not because they're not human-centric, but because they just aren't as good. So should we just get rid of static analysis?
I think there's a huge, interesting research area there to figure out how to make the output of static analysis tools work for people.
$1 million question.
Wouldn't that be fixed by just telling it's configurable? So
No. No. Okay. Do you want to add, Patrick, would you like to answer the question?
No, you're
No, I think it actually, so various things that you can imagine, right? What was the programmer last doing that resulted in this long list of errors? Can we tie those things together more, right? But there's lots of ways that we could understand more of the context of why did they run the static analysis tool to try to tailor the results. And it goes a bit beyond just saying, well, we need a different interface. I think there's more understanding of what they're trying to do, more automatic determination of what they're trying to do that could actually tailor the results. But Patrick has a different answer that he'll give you later.
No, it's like, okay, so it's hard to tell what's there's not, as Gail said, there's not enough information to know why it is that sometimes it's a false positive and sometimes it isn't, right? And so you really do need more context. It's not just, you can't just say, go by type and say, this is one problem that you don't want to care about. That's sometimes the case, but often it's like, you just can't tell and you need more information.
But that's actually a really good point in the sense that when I say that these tools are ineffective, it doesn't mean that they always have to be ineffective. These are opportunities to try to learn what we can do to actually make them more effective.
So,
There's dude.
well, I'll ask a question. So you talk about assessment of effectiveness, right? And there is a lot of interest in the community to assess that, yes, our research really is making developers more productive. And so now you've got all these researchers trying to engage with practitioners and say, use my tool, use my approach.
Yep.
We're going to improve your work, right? And so now they've got 20 people
At them.
At them.
Or asking them to answer
Tools,
surveys. Yeah.
So, is there a development, chain that you do internal assessments leading up to working with practitioners, or do you just have a relationship with industrial partners?
We value our industrial participants really highly. So we don't tend to step to doing that industrial assessment until we've gone through lab studies and stuff. So yeah, we see it as a pipeline whenever we can because they're really valuable. Wherever possible, we try to do it as a collaborative. So we have a collaboration going now where some work what we've done on bug triage for quite a number of years. We now have an industrial partner who really wants to use it, and we're doing co-development of that, and that's really exciting.
The thing is, to answer the question, the way software works these days, when you put it out, it's going to make or break. You put it out, people start using it, word gets around, oh yeah, this works or it doesn't work, and then it either takes off or it doesn't.
Yeah, but I'm a PhD student, I don't have time to wait for that.
Yeah, but the thing is, I see the assessment as more of a tool to help you get it out right the first time rather than as an advertisement for the tool. In other words, as you're developing, you assess with as much in situ as you can so that when you finally get it out, you know that it's the right tool, and therefore it will take itself out. It's not going to be accepted as an advertisement. Hey, take our tool because in this assessment we did that. Nobody's going to pay attention to that. So use it as a tool to use it as a way to get the tool out right the first time.
And by no means do I expect that every PhD student in tools is going to get all the way to a field study. Did you have a question?
Yeah. Just out of curiosity, what sort of increase did you have for those 13 people? Like, was it like?
It was actually pretty dramatic. It was statistically significant, and I seem to recall somewhere between roughly 20% and 90% improvement. So yeah, and to me the real why does it work? People still use it. But people, I can come up with any measure, frankly, that could show you that it would use it because I can define the measure because there's no standard ones. But if people are choosing to use it, then it must do something. Yeah.
How long do you think it will be before this approach is used in other domains, such as in a doctor's office or in somebody fixing a car?
That's my dream. In the first years of our company, when we were a little smaller, I actually used the tool to manage the company with everybody else for about 7 years. And that was Word documents, Excel documents, web pages we had supported so you could find particular parts of a structured web page that related to a task. I honestly believe that it can provide results. We have some data over about 5 years of use that shows that. It's really hard to get people to change their behavior. So unless you can model a lot of the information that they're working with, it's hard to get that next stage. But trust me, that's still our dream, for sure. Change how knowledge workers work. Because it's really ineffective right now, how they work. Yeah.
Does matter somehow keep track of the path that the developer takes? So like keep track of from which source file someone navigated to another source file or something like that. So can like make suggestions after working on this file. Probably want to go here or something like that.
Yeah, some of that information is available. We tried a lot of different recommendation approaches. So my group does a lot of recommendation stuff. It's really hard to get people to use the recommendations. So we had kind of a related thing, where it would recommend people who had looked at this file also go to these test cases. We've done web pages. If you've searched here, then you're probably going to go search there. You can show effectiveness for little bits of time, but it's really hard to get people to care about recommendations in the context of their work. So it's a huge open problem. No offense to people who do recommendations in the audience, but a lot of the recommendation systems work is about things like books and movies and places where the penalty of a wrong recommendation is somebody goes, that was a bad movie, or that was a bad book, or they're looking at the recommendations in Amazon and they go, that book cover looks interesting, I'm going to look at that one, right? When you are stopping somebody or showing them a recommendation as they're doing a heavily cognitive task like programming, wow, it's a really high bar. Like anything that's wrong, they're like, this thing's a piece of crap, and they throw it out. So we've tried longitudinal studies in undergraduate software engineering courses. We've tried, what I've learned is it's hard. Delivering the recommendation in the context of work is hard. And I think there's a huge research opportunity to make that better so that we can actually make knowledge workers work better.
But in general, it keeps track of the data, so the data...
Yeah, it's all, yeah. Yeah.
Thank you for coming.
Thank you.